Good morning, and thank you for your comment. I've read through your response, and I've come up with what I believe to be two areas that I would like to address. The first one pertains to observer height and obstruction height. So let's get into it. So in my first response video, I covered bulge height, which was the distance or the height of the sagitta, which would be from this point right here down to the cord. And it was a 10-mile distance that you had provided, and I had calculated roughly about 16.67 feet. And so that had nothing to do with an observer or what you should or should not be able to see at a given target over that distance. Now, this heavily depends on the location and height of this observer. So we're going to plug in some assumptions, and I'm going to show you a quick and easy way to calculate an approximate observer height slash obstruction height formula. First thing that I'm going to do is I'm going to cut this in half at the point of tangency. And we're going to calculate this side first based on this information and an assumption with the observer height. Be clear about the observation height. The observation height in this example is 0. Basically, you are at sea level. Now, sea level does have a height associated with it, but we can get into that later. I want to keep things simple here. So we're calling the observer height of 0 and the eye height of 5 foot. What that means is from the surface of the ground that you're standing at to the center of your eyeballs is 5 feet. So what we'll do is we'll set the problem up like this. This 5 feet is the observation height plus eye height. There is no observation height. There's no height above sea level. You are at 0, so it's only the eye height. Then what we do is we divide that by the amount of curvature, the rate of drop, so the 8 inches times the mile squared, plus shaving off roughly 1/10 for refraction. It's a just general standard rule of thumb at sea level, and then we take the square root of that. So let's take our eye height of 5 feet, enter that in. Let's take our C plus R formula, our curvature and refraction correction, which is 0.574. Let's divide that, and let's take the square root of that. And that's what we have. This gets us from here to the horizon. Now we can address the other side here. We got ourselves to the point of tangency over here. Now we want to know how much of a target should be obstructed by the curvature of the Earth based on this distance and this observation height. So what we're going to do is we're going to take the leftover piece that's in here that got us to the horizon, and we're going to subtract that from our 10 miles. Let's get our 10 miles in there. Let's roll that up, and let's minus that out. And so we've got 7 left over. But what we need to do is we need to take that leftover distance, square it, and then multiply it by our correction, our curvature correction, and our refraction correction. And that was the same number that we used over here. Well, let's take the leftover distance and square it. And let's multiply it by our drop formula and correction, 0.574 times. So it looks like 28.5 feet. What that means is if you have a target over here, approximately 28 feet, so this distance right here, should be obstructed by the curvature of the Earth. Let's assume for a moment that the target is actually a building, and you're standing over here and you're looking across this 10 miles with binoculars or something like that. And there's this building over here, and you can only see these 2 floors of the building. However, where you bisect the building with eyesight, with your line of sight here, you bisect here, there are 3 more stories, assuming that each story is roughly 10 feet, that you cannot see. But let's say from your location, you wanted this window to appear here to where you could see it, you would have to make a correction, and that correction would be the the C plus R. So you would have to use this 0.574 to make the correction for what the Earth is doing over that distance. So this departure that the Earth's surface has from horizontal at sea level, you would have to make that correction in order to get this floor to appear where this floor is. Okay, so let's take a moment and let's address your next claim. I believe what you're claiming is that the horizon always measures flat. So let's get into that. Now, in my experience in measuring a dip to the horizon, I measure a curve or the horizon falling away. I've never measured the horizon always flat, as you put it. And so this is a field book. I'm going to use this as an example here. This is where I record my data from flat Earth observations and measurements that I make. This particular one I'm going to use is my most recent. This was on Sunday, March 3rd at the University of California, Santa Barbara. I set up over a geodetic point called Pelican. Here is the identification number for that. My instrument height was 5 feet and the height above sea level was 39. And so this is how you set this problem up. Here are my results. And so we're going to go over this information over here. So let's go over a few things here. This is the radius approximated, or an average, and this is the radius averaged. This is my height above sea level. This is in feet. This is in miles. So we need to do a unit conversion here to get into the same units of measurement. This is my eye level. And basically, if I took and turned from eye level down to the horizon, I can predict what this angle is going to be if I solve for this angle here. This angle and this angle is congruent. Basically, if I solved for this angle and I added it to this angle and subtracted from 180, I would get this angle. So if I took this angle and minused it from 90, I would get this angle. First, let's solve this side of our triangle. Let's take 44 feet. And let's divide it by our unit of measure. How many feet are in a mile? And let's add that to 39.59. So now we have this side of the triangle. And these two added together in miles would be our denominator here, which would be our hypotenuse. You can see we have a 90-degree angle here. This would be our adjacent side. This would be our hypotenuse. So we would use the arc cosine function. This is how you would write that out. We're solving for this angle here. So now let's take this side of the triangle and divide it by this side of the triangle and hit our arc cosine function. So we'll take 39.59 and we'll roll that up. We'll divide and we'll take and hit the arc cosine. And so that's our angle. That's theta here in decimal degrees. Our angle in decimal degrees, we want this into degrees, minutes, and seconds. You can go a couple routes on this. You can just use the base 60 system and multiply this out. Or if your calculator has the ability to convert it like mine, you can just go. And so that's what we should measure to the geometric horizon, which would be 7 minutes and 3 seconds. So that's what I came up with over here. That gets me from eye level to the geometric horizon using these numbers with this geometry. However, I measured to the apparent horizon because refraction is a thing. And so what I did here was I took how we get refraction. It's just the radius of the Earth divided by 1 minus k. I used a 0.17. You minus that from 1, you get 0.83 or 10 inches. Divide into your radius. This becomes your new radius now. Here is the prediction that was given to me using a refracted radius for where the horizon should be measuring. And here's what I measured. And so how far off are we from what I measured to the geometric prediction? If I take 90 degrees, 7 minutes, and 3 seconds, and I minus out 90 degrees, 6 minutes, and 28 seconds, I end up with 3.5 arc seconds. In closing, I used the radius of the Earth. I took into consideration refraction, and I made a measurement from eye level to the horizon, and I came up with a prediction. Then I was able to actually make the measurement, and this prediction that I had with refraction was 6 minutes and 26 seconds. I measured a 6 minutes and 28 seconds. So the question is, where does the Earth always measure flat in referencing an angle from eye level to the horizon?